we are getting positive quantity. So what you see when you do the dot, you get the normal component. Tangential, you get the normal direction. What if you do the normal direction? So next time it will be the for normal to normal, that will be the minus I. So what you see plus 90 degree. Whenever you taking the dot, I dot j dot, you see the angular velocity in direction plus 90 degree. Okay, in this way you put it. So we are done. So now P is the general vector. It could be velocity, it could be any vector. It's not just define the position, velocity, anything. Okay, so translation dynamics. So what I am telling now, F, see this was earlier with respect to inertial frame. So in inertial frame, now I have decomposed into body velocity and this Coriolis system and this force. Now this force I have to take equivalently to the in the body frame. So for quadrotor in body frame, what type of forces are working? Why did we kick out aerospace engineer? Because we have to just work with thrust. Okay, thrust and torque. So we kicked out aerospace engineer because we told, okay, we understand the thrust. Now we just change the RPM. If I am talking about RPM control quadrotor, I change the RPM, I know what is the thrust. So someone has given me curve relation between thrust and RPM. Okay. So this force, we have only gravity force, and so gravity force works in the different frame and the thrust force works in a different frame. So now if I define velocity UVW, it's in body frame, angular rate PQR. Remember, this is also angular rate in the body frame. This is our Fxxy, Fz in body frame. So I just substitute and solve, I'll get this term UVW 1 by m, this forces acceleration, that means, and this is a Coriolis system, okay, due to the rotation. If there is no rotation, you don't get this term. Okay. So now don't afraid from this term. Next time whenever you see such equation, you have to just do one cross product, write I electrical engineering IJK UVW PQR, okay, and then you know how to do the cross product. You can write here this term, and here only you have to write the forces. Okay. Why it's not working? Changing here from here slides. Okay, rotational dynamics. Similar to translation dynamics, we have to apply the rotational dynamics. So angular momentum conservation. So change it. So this again same formula. Seen in the inertial frame, one component in body frame, and this is a Coriolis system. Okay. Now H is what? What is H? Angular momentum. Okay. That is I omega, j omega things. See, linear momentum and angular. So wherever linear momentum was there, angular moment you just substitute there. Okay. So next, now J is inertia matrix is not changing. See, battery you have put at particular position, change in mass is little. So the configuration of your quadrator remains the same. So your inertia matrix is not changing. So J or I, whatever you say, it's not changing. So it's not, we don't take the dot. And then omega, it's again this, and this will get these things. Okay. And this is, I have done how to find this inertia matrix. So quadrator is symmetric things. Okay. So if you see the tensor of inertia or inertia matrix, so tensor of inertia, if you say it's more appropriate, but as a electrical engineering you tell inertia matrix, it will work out, we are not serious, only we have a diagonal term. Okay. But if you want to find how did it come, you just write this formula, angular momentum. So you know R into cross V dm, and then V is R cross omega. You substitute here, change the cross product to dot product, substitute here, you put everything here, do the little algebra, Ixy, Iyy, Ij, you moment of inertia. If you have this term, you can find this analytically, and there are some term, this product of inertia. So quadrator is symmetric. Okay. So these terms you will have a 0. So you will get this is a matrix. Okay, if someone is working in a fixed wing UAV, they can use this term. And also that there will be particular 2 terms will be 2 or I think 4 terms will be 0. Okay. So this is the inertia matrix, and these are the some things not useful for aircraft problem. This will be useful. Okay. And so now gravity is working in the vehicle frame or body frame, in inertial frame, and all the force you are transferring to the body frame. So now we have a transformation matrix that big. I was telling about DCM. So I'll just multiply vehicle to body, these 3 components I'll get it. So when you have seen fx, fy, fz, one of the term will be this, all 3, like one of the column. And another column, can you tell? See, there will be 2 column. One is associated with the gravity and another associated with the thrust. Okay. Gravity I have told. Which will be another one? Only I am checking whether you are here or not. See, vehicle is like inertial frame. Vehicle frame is nothing but just inertial frame, but you have CG you have transferred to, the origin you have transferred to CG of the vehicle. Okay. So mg is always working downwards. So we have assumed flat earth. So happy we have got a static space representation finally. So this 6 was easy, and now T by m because of thrust. One term because of thrust, force is acting in the body, another due to gravity. This is Coriolis term. Here only diagonal element, this is a Coriolis term, and LMN, this is a pitching moment. Okay. So we are ready with the now equation of motion. Now next things, now the problem is that these are the equation of motion. You have to design the controller. Or first you talk about stability. How will now I will talk about stability. Now I am putting the head of control engineer. All mechanics work is done. We have to switch the role. Okay. Control engineer, and now we should be fast. If you have to see some interesting things, this should be fast. Okay. So first I have, how many inputs do we have? How many rotors do we have? 4. So 4 control inputs. For 4 control input, we have translated into thrust LMN. More specific form I will tell. And how many freedom we have? X, Y, Z. Yeah. So this is an under actuated system. Okay. Unstable under actuated system, we should be excited. Control, yes, we have got something really to do. Okay. How do we control? Already morning when I was giving motivation, I have already talked about this. Okay. Now we have to talk about controller. Yesterday Abhishek told stability augmented system, control augmented system. Now you tell, I have given you the equation of motion. Your friend told, okay, I will give you. See, you usually do in the course this, what you can say, spring mass system damper, right? There is no control. Then you derive the transfer function and teach the student. Now I give this whole equation. I have done the whole dirty work for you. Now you tell me how we will design the controller. The basic controller, whenever problems will come, if you are, what do you think, simplistic form? PID. Okay. But these are the nonlinear equation. Okay. So is it okay we work with PID, or we have to see nonlinear, or we just with one nonlinear, or we see many nonlinear techniques? Because we have 4, 5, 6 students, and each student we want to give up one problem. Okay, we'll see. I don't know. So this is RPM control quadrator. So thrust is related to this. Okay, and LMN. So moment, see 1 and 3. See if the difference 1 and 3 was diagonally opposite. So if angular speed will be different, it will do the roll. Okay. So remember, extend your arm. Okay, and if angular velocity is more, raise it. Okay, you will going other side. If angular velocity is more, you raise this hand. So you are doing this motion. Next, M, pitch, I don't have hands, only 2 hands. So pitch, you have to understand, you are doing head motion. Okay. So you assume now, because assumption, because under actuated system there is a one motor running forward and one backward. If you have a thrust more, you will go in other direction. If thrust is other, reverse is back, you will go forward direction. So now at least that physical understanding should be there. Okay. So if you can relate, these are the two moments, and this is due to the torque. Okay. And these are the some constant. So yesterday if you remember, you have seen this RPM versus thrust curve, but it was little bit more complicated because pitch angle was there. So in this quadrator, pitch angle remains same. So you have to find this coefficient experimentally, or sometimes you can find theoretically also. Okay, this constant. But again, we are lazy people. We are engineers. We want to do minimum work. Why do I worry about this all omega 1, omega 2? Can I do something more? Can you give me the formula in terms of PWM? That's what so someone tell the algorithm, someone tell okay some algorithm TLMN, and then I will just change I'll give ECS my PWM. So same matrix is related what I have solved for omega 1 square, omega 2 square, omega 3, omega 4 square. So it's inverse, and now omega, that RPM I am control using the PWM. Okay. So if now you want to control your quadrator, you have to get everything from the Hobby Kings or some local supplier, install motors, connect ECS, put the Arduino board or something, Pixoc or any board, and write the algorithm. That is the heart. If you can write smart algorithm, you have done the good work. No one will care what you have, just you have to do the assembly. But the main work is the algorithm. And the heart of the algorithm, if you know some magic formula to achieve what TLMN, because these are all the constant, if you know TLMN, you know what pulse is the given. So your job is done. It's as simple as. Now objective is that how do we get TLMN? So first we think about stabilization. What is condition of stabilization? Now you tell me, I have told everything. Okay, what is the condition of stabilization? T equal to mg, LMN equal to 0. Okay. So now you have to find these are the, but when they are deviate from this condition, you have to bring back into that condition. That is your steady state condition. T equal to mg, LMN equal to 0. If there is any LMN, they are not the, you can see overflight or the steady state condition. So how will you compute? Let me see what is there in next slide. Control philosophy. So we have to use force balance, thrust support the weight, moment balance, so pitch and roll rate, and torque will for yaw. Only these three magic things is there. Thrust equal to weight. So you know only you have to do roll and pitch, that will be controlled by differentially, that formula second and 2 in the couple of slide back, and the last you have seen W1 is square, W3 square minus W2 square, that is for yaw. Okay. This is a philosophy. Now use any control algorithm, I don't worry. You use sliding mode. If you want to make impressive things, you can say matched uncertainty, unmatched uncertainty. If you want to use backstepping, you can use adaptive backstepping, but philosophy remains same. Any control algorithm. Okay. So we start with the simplistic form, I think. PID. PID very simple. What? Error, derivative, rate of change in the error, and the integral term. Okay. And we will see dynamic inversion approach also. So inner loop. See, first thing is we want to stabilize. We will see other things. First we want to stabilize the vehicle. We don't want to break the vehicle. So stabilization, when I tell stabilization, what does it mean? What physically you tell stabilization means? moments, okay, but my vehicle does not under moments. In layman terms, see the word you have told, it's right. Can you identify yourself who told this moment things? See, it's very simple, intuitive things I want. See, moment is like little bit, it's hi-fi. Okay. Stabilization. So, see, we tell attitude, we have represent Euler angle, right? If we say I'll give the some bank angle, it will start rotating like this. Okay. If it forward, it will go in forward flight. So that is also stabilization. If my bank angle or forward angle is some constant angle is there from constant velocity, that could be the one of the equilibrium. Okay. If it's doing the circular trajectory, it could be the one of the equilibrium. But I am talking about equilibrium. So my attitude remains, whatever attitude remains the constant. It does not rotate these things. Okay. So where is change in the attitude, I bring back. So I have given the hover condition. If it slightly deviate from this, you restore to the same things. So how do you think it can happen? Change in that. Now this is the crux of the inner loop design. My attitude is disturbed from the equilibrium position. I have to change my attitude. What I have to do? See, just will think first this disturbance. Okay, this disturbance. If there is a disturbance, I have to apply some restoring force or moment. I'll tell moment. Force will generate the moment, but I'll tell the moment. Okay, we are inner loop because so now when I talk about inner loop, I talk about stabilization. All I'll talk about the moment, because see we are soon you will see we are working with PQR. But if you see loosely phi double dot, theta double dot, and this psi double dot, they are related with PQR. So what I am telling, see that is what your one of the variable this role is deviated from the equilibrium position. So the error will be introduced as right. This introduced error I will take it, and I know LMN is this. Now what I assume when I do this PID is linearized things, right? Linearization things. So whatever in the morning or first half we have done, we assume the vehicle has a 3 different frames. Okay, first you do the yaw, then you do the pitch, and then you do the roll. Now I assume as a controller, I push my problem on controller. I assume my body rates are similar to the Euler rates. Okay, so that's what I assume. So through this assumption, I write LMN dot equal to this. Okay, so from this error this PID formula I have got. So what is required LMN I can compute. So here there is no error in the first 2 channels. So what you will see, it will require L. If there is here is a typo. Okay. Okay. So now you understand LMN. So there is a disturbance in the rolling moment will require. There is a disturbance in pitching moment will be required, and there is a disturbance in the yaw moment is required. So it's pretty straightforward. It will work, and there is no magic in this. Okay, it should work, and because you are disturbing from your initial position, we are not talking about highly maneuvered things. Okay, so stabilization is done. Okay, now we don't have to, but only these 3 things. Under actuated system, I told we have 4 motors, 3 conditions. Still one things we have to do. That is we will see in outer loop. Okay, now position hold. See, I told we have a 6 degree of freedom. So 3 input already I have used. You think or you assume in producing LMN. Okay, because we have 4 motor. Using that combination, we can only satisfy the 4 equation because linear things. Okay, so but my problem is that I have to control the position in terms of x, y, and j. Okay, so one things I can tell, I do not worry about x and y, only I worry about g. Okay, so whatever error in the g, I can compute thrust like this. Okay, so the whatever thrust is required, this will come. So now I will plug thrust, Lm and n in that formula. So I will know what is my angular speed is required and what is a PWM required. But for stabilization it's okay, but someone tell no, I want strictly position hold, y and x also you maintain it. Okay. So it's under actuated. I will start scratching my head what to do. But luckily morning when I was giving talk, what I told, if I have to move in x direction, now physics, what I have to do, I have to pitch it in the y direction. If I have to move in y direction, so now you see xy error. So why I am relating error in y with the roll. So if I do the roll, what I'll move in direction. If see I'll roll it, which direction I will move? Y direction. This is a rolling y direction. See, x is a forward things. So just you understand this. This is all physics. If you understand, you will understand. The moment I will, I'll do the roll. I'll go in the y direction. So there was an error in y direction, and I asked to move in the y direction. So by intuition, it should this error will go 0. Then there will be no movement. It will restore. Okay. And similarly, in the x direction, I have to do the pitch. Okay. So it's look ulta here. Okay. It's look ulta. So in some of your math problem, you see the cross product. You do the cross product, right? So here they are closely related. You remember, because you move in whatever or you tilt in direction, you do the opposite. Okay. So this way it's related. Now, anyway, if you see the previous slide, we have to give this phi t and theta d. Okay. So this outer loop will give the command to inner loop. So using both loop together, you can achieve the position stabilization and position hold and stabilization as well as well. So is it clear to all of you? See, if you understand, then we can move into nonlinear. This is like very basic and it's very physically intuitive. So just revise one more time. See, if there is a, I don't say there is an error, I want to move in the y direction. Okay, what should I do? I rotate around x-axis. X-axis, that means what I'll introduce roll angle. So now you assume that there is an error in the y position. So what it should do? Inverse engineering you do. It should give some roll command for, okay, and that roll command is computed using here. Okay. Similarly for pitch things. So now you know how to control. So inner loop is a pretty forward. Okay. Yeah, you are now you have some outer loop design. It will tell how to give x, y, x for control input. Okay. What input we have to give? Z. Okay. How do you control Z? Then psi. Okay, x, y, z and psi, x, y, z, because outer loop you are x, y, z and psi will be given by outer loop. Okay. So when we will see the one problem today application, there I will tell we put some guidance algorithm similar to what Professor Ghosh discussed. So that algorithm will tell each instant of time what will be your required x, y, z and psi. Now that you can feed into our quadrator control algorithm here continuously. That will move according to that. So you have integrated guidance and control problem. Okay. Or similarly, you can some things you can do here also. This law you can change and you can solve the integrated guidance and control problem. So this is a stabilization problem. Now I want to do the tracking problem. Can I use the same code for tracking problem? See, by default, engineers are lazy. They don't want to change. They don't want to write different MATLAB file, script file or anything. If they think some things, same thing what can work, they want to use it. Okay. So now I want to do trajectory tracking problem. Can you give me some idea? Now you are controlling. I am coming to you for asking solution. My work was done. Exactly. You cracked the problem. Say you have trajectory. So only things problem could be you know the x, y and g position. Okay. So maybe we'll consider case of 2D. Z we can make 0 or Z or some things. We are working in 2D problem. X, y and psi you can give. Okay. Once you give x and y and psi, the quadrator is supposed to follow the earlier our x, y and z, if I was at origin or I was at some reference, it should maintain there. Now you are giving the x, y and psi is time varying. So same code, only you make the x, y and psi as a time varying, you are done with trajectory tracking. So I have solved now stabilization and tracking problem. Yeah. Yeah. Yeah, desired. Now I have not put in slide in bracket T. Okay. So that was implicit, but now I have made it explicit. So I have revealed the magic. So you have solved the problem, but what was the problem here? Everyone thing was okay with PID. Why do we want to do nonlinear control design? What is x, y and z is important, and what else can be important? If we have a position, what else can be important? Okay, you are right, partially right, but I am looking something more answer. See our space mission and you see launch vehicles, everything is working on PID, but still we want to do nonlinear. See, it's not, see, okay, partially you have answered, okay, PID, maybe see, this may be true, we are when assume small disturbance may not be true, so we may have to use the series of PID controllers or gain scheduling, if you have heard. So same gain may not work for the whole problem, or if I do more formally for all flight regime it may not work. Okay. So you have to choose the series of, and second most important reason, you are not happy with PID because you want to show non-linear control design works better than PID. But just joking apart, see in this formulation we assume that body rates and Euler angles are aligned. So we are violating. So maybe PID try to compensate this, may achieve the job, but performance will be not good. Okay. So now I have marked the problem or highlighted the problem. So next to go to the nonlinear technique. Any question? Although you are, yeah. Yeah. Okay. So see, this is a assumption we have assumed. It works. The perfectly, it's mathematically, it's not like. See, we have done the approximation. Okay. From our physics, we understood this work like this work. So we have generated reference. But when you put into this equation, 6 equation, when you got the solve for TLMN and you put that equation will be not satisfied. Only 4 equation will be satisfied. 2 equation will be not. For linear case may not be all equation will be satisfied, linearized case. So it looks, it does not under actuated, but this was the trick. See how to control under actuated. Say aircraft is by design is under actuated system. So we always do like this. This is a trick. Generate the reference for Y and J. That reference may not give the good performance, and as a control designer, our job is to find an algorithm which can do in a good way or better way or best way. So because now we have an algorithm, now we know the solution, so it will no, it's not under actuated. But by design you have a 6 equation, you cannot satisfy. So you are using the intermediate things to achieve your goal. dynamic inversion approach. How many of you know dynamic inversion approach? Okay. Do you know feedback linearization or dynamic inversion? So this is dynamic inversion approach or feedback. I love it. The thing is that the good things about is dynamic inversion approach. Anything, whatever controller is given, if I consider second order system, I can make it as a pendulum, or I make a second order mass spring system. Why? Using the nonlinear control, I can linearize my, or closed loop system is linear. So the idea is that in this dynamic inversion or feedback linearization, so you cancel all the nonlinearities, okay, through your feedback action. So it's feedback linearization, it's also called dynamic inversion. So there are communities, someone would like to tell dynamic inversion when they are doing the output dynamics control, and when you are doing with all the system, they will tell feedback linearization, but more or less they are same, or not more or less, you tell exactly they are same, only the way, the concept is same. So if we choose your control and cancel all the nonlinearities, what will be the requirement if you want to cancel the nonlinearities? Control person, you should be able to tell. See, I must have plant knowledge or plant dynamics. If I want to cancel some things, or I want to beat someone, or I want to defeat someone, I should have a knowledge of what his power is, that his strength is that. Okay. So if I want to cancel the nonlinearities, I must know the plant dynamics. Okay. Okay. So philosophy is that cancel the nonlinearities. Okay. So the control design will look very similar to PID, and the purposefully I have put. Okay. So this is the inner loop. What I will tell it's very simple. I have told you whole things I will do you can say mass damper system. I will not go more than second order system. Okay. E double dot 2 zeta omega n E dot omega n square this is the equation. If you know, you love it, you can solve the problem. Okay, you can tell anything about this equation, whether it's stable, non-stable. Omega, zeta. Okay. So first things I can characterize in terms of zeta and omega n, second order system. Okay. So what this everyone teach, right? Control curve second. So what is, see, we have under damped, over damped, and what is else? Critically damped. Okay. So what is stability? Okay. Before that, first second order, let's see first order also. It's very simple. We will be using this also, don't worry. These two equations we will use and will design our controller. When will be this system? E dot equal to plus Ke is, or E dot equal to minus Ke is stable. K is, if we choose the K, whatever E is there, we don't have to worry. E will definitely go to 0. Now error, I am defining error. Okay, E is my error. That means if I define E some x minus xd or y minus yd, z minus zt type of things, or phi minus phi d or things, if first order, if I satisfy this equation, okay, so it is guaranteed. It's how fast it will go. It's exponentially fast, or it's asymptotically, or what is a convergence? Exponential. Okay. Now coming to second order system. Okay. What about second order system? You know the response, you know the solution. zeta omega n should be positive or negative, that only you have to tell. You know the flight envelope, right? So you know it positive, half, negative. Don't make me to tell everything. Please tell something. So that means we know the zeta omega, and purposefully I have written in these terms because tuning will becomes very easy. Okay, you zeta you choose 0.7, then omega and you play around for 5 value, you will get definitely, I will tell you will get definitely the good tuning. Okay, so I told my controller or my control design, okay, in this time I told my student, why don't you choose these things? Okay, only things you put 0 here, take bring each term. So second order, so I choose my second order stable error dynamics to synthesize a controller. So psi d, it's a desired value. This will be given by user or will be given by the outer loop. Okay, so last term will be given by the user and first two term will be given by outer loop. So again stabilization similar here. So zeta and omega n is my tuning parameter. Now if you remember, when we derived the equations of motion, this relation we used it. Okay, you can switch off the lights. So if switch off. Feedback is not right. Extremely poor. Yeah. So if I take the double derivative, if you see, okay, I am introducing the idea of relative degree without telling you, although I have told you, but I am not telling you directly. Okay, if I differentiate one more time, so once I have to differentiate here, I can keep constant here, p dot q dot or r dot. Okay, so p dot q dot or r dot, there is a terms, if you remember in equation of motion, lmn. Okay, so then I can put this whole terms in the here, and every terms I can take the right hand side except lmn, and lmn only things what ix and iy. So I will do this. So I have not shown the messy algebra here. Okay, so see, I am PQR, I am writing the expression that will be the all right hand side. Okay, lmn you will get like this. So Coriolis terms and this. Okay, so that is lmn. So if you remember my PWM matrix now, each time when I will tell lmn, you have to remember my PWM. That's what my ECS will do. So 3 terms I have already got. Okay, so I have to put one more term, that is T. So now I will come for the outer loop design. So where I want to maintain. So position control. Okay, so we can do with only Z, but we will doing XY again. So again second order error dynamics. Okay, again my zeta and omega n is easy to choose, easy to tune. Okay, I substitute you, and this is T, ID, and so we have algebraically solved this. And now if you want to relate this with the PID, see there were some approximations here. If you remember, this approximation here were used. Only now we are this approximation. Why we seeing this complex term? Because now we have not assumed that our Euler angle are aligned with the body rates, change of. Okay, because of that you see this term. Okay, now if we substitute this control into our plant, you will see it will become the second order system. Everything looks linear. So that's why they tell feedback linearization or dynamic inversion. During the control design, you are doing the inversion, you are cancelling the non-linearity. Okay, but philosophy remains same, right? Stabilization and position control, we have not done any magic. Just second order error dynamics we use 2 times and do little algebra, that is we are good in the control people, we are good. So next what is there? Now this is architecture. Okay, at least I have a, you can say, honor to show one block diagram during the presentation. So far I have not used. So this reference command, who will generate? So this will generate some outer loop, but we'll say this is guidance, and we will see today. See, remember here, okay, xd, yd and zd and psi d, and later on I will tell zd I am holding constant. Okay. So only three things. Zd I can give 0, I can give 5 meter, 10 meter, whatever plane of the operation I can define. Okay. This is a position controller, so it will tell what thrust is required based on the z, and whatever x and y is required, it will tell my rolling and pitching motion. Then you give in the attitude loop controller this roll pitch here, and you will generate the LMN and T. Now morning someone asked my x configuration plus configuration and whatever configuration is there. I have to just know TLMN. Whatever configuration is there, you can define control allocation. Okay. So you can have a different axis. Okay. And now in break, one of the audience asked if I use 5 rotors, 6 rotors, 7 rotors, you can use as many as rotor, I don't worry. All will go in this control allocation. What you require TLMN. If you try to solve using little bit intelligence, all the difficulty as a control engineer you were facing as a physics, you can push into here. You tell don't in terms of PWM, now you tell in terms of TLMN. Only slight modification if do you in your approach, you will be the smart. Okay. So control allocation is nothing but that matrix I was telling. Okay. And that matrix change with the configuration, with the number of rotors, okay, and the design. But the solution approach does not change. So are you happy? Okay. So now is plant, but in block diagram it looks okay. But you want to control, when you want to control, you have to estimate your these states. How will you estimate these states? Can you tell me how do you do? See, I have told the flight control design, I am not telling autopilot. Okay. There is a difference between autopilot and flight control law. I am so far, although my title slide tells autonomous, I am cheating little bit. How do you estimate? Yeah, sensor. Yeah, sensors and some filtering algorithm. What I do, I tell Abhishek, give me your autopilot. Abhishek is my colleague. Yesterday, give me your autopilot. I have a control law. I will put control law. Already you are doing anything. So we work together, and then we can validate the algorithm. So if you are working, it's good idea to collaborate. If someone has designed in your institute, your place, or if you want to collaborate, so if you are designing flight control law or someone has an autopilot, so you just change the code. So you will get the quickly this algorithm. You don't have to, each time you don't have to work. So there are board, Arduino's board, there IMUs is there, so you know accelerometer like things. If you Vicon system, it's very expensive. I don't think in India many places it's there. Only IIT Kanpur where you can get the accurate positions. From position you can extract the velocity, but if you are working outdoor, GPS you can get the value with IMU. So once you know, make the platform, although I work with the dynamic inversion, you can now switch to the same philosophy with back stepping, or you can use the sliding mode control law, any control law. So this two block diagram will change it. Okay, the control law. So it's quick to validate the algorithm. If you want to do some extra things, then work in this block also. Okay, how to generate the guidance command. Like now you want to do consensus, rendezvous problem. You want to come together. So this will tell how your x, y and psi is evolving. Okay, if you taking only holonomic system, x, y, how is evolving. If you take the missile problem, same architecture will be there. If you take pursuit evasion game, that I will discuss also. So bit interesting. I love that, so I am presenting that. So do you have any question? Next I move. I don't have any simulations results. Okay, very nice question. See, that's why I told my dynamic inversion will convert everything into the second order problem. Okay, so mass, you are cancelling the mass in the inversion. Okay, so this algorithm in theory it should work. Okay, in practice you may face little bit tuning problem, not major. So maybe for 0.1 or 0.2 you have to change the things if you are changing, because see this inertia matrix like ix, y, y, z, na, if you are changing, so tuning depend on that also. So little bit you have to play around, but not much. But ideally you are converting every system into second order problem. So there will be not a problem. And believe me, if you are using this tuning process, zeta 0.7, omega n in range of 1 to 10 will work more often than not. So all your tuning problem will go up. Okay, ask your student, ask or you do, first set omega n equal to minus say 1, change 10, 100, change the order. Once you change the order tuning, you say converge on 10, play around 10. Once you change the order, once you do then you do the fine refinement. So it will be easy to tune also. Okay. So then what we thought, once one of my master student did these things, so he was doing, so we told this attitude things, na, if we design autopilot, one thing he told me, sir, in autopilot if you use this so many cos and sine term, they are to only 10th order approximation, it may not be right. I told 10th order is enough. Why, what is the problem? No, still some problem or like that. Then I told, and he told I don't like second order things. Na? Okay, I told okay, we'll do it in intelligent way. See, anyway we want to do attitude stabilization. So attitude stabilization we can do in a two way. One thing, use the attitude, or through the rate. We can through the rate feedback also we can send. Okay. So whatever we have a attitude angle, convert into the rate things. So first I will show how can we do, and then how we from the second order system, because now we want to work as a control engineer with first and second order, because we don't want to like third order system, there we cannot solve analytically. Root Hurwitz table, who will draw root Hurwitz table and find the gain and other things. If first and second order is there, we know the time response. So we can say what is the time constant, gain, everything. So what we did, okay, so the idea is now I want to work with only this body rates, P dot Q dot R. So what I'll do, P minus PD, similar to all three equations, okay, K, P minus PD. Angular rate feedback, okay. I don't want to do attitude. But problem is that I have a attitude, I don't have angular rate. How to compute this PD, QD and RD? Okay. So what first I'll tell, okay, I'll design, say I cannot get away from the whole the problem. So if you see, if you want to write a state space representation, you have nth order system, you decompose into the n first order system, right? So I told, okay, let's do that. So what with P, what is associated angle? Okay, this is the first order. Okay, attitude controller. I'll simply use the attitude controller. Now I write phi dot equal to phi d. This k, everywhere I write k, they have a different values, not same k. Okay, I am overwriting. If you work on the programming, you know overwrite. If you have worked with C, C++ overwriting operator, so I take the liberty to use this k. Okay, k. I want to use plus only. Okay. And do you remember formula for PQR in terms of phi dot, theta dot and psi dot? Okay. See PQR. Okay. You can switch off light now. I won't go to board again. there is a delay also. Should have worked on control delays also. Okay. So see, now I know these rates from this first order dynamics. Okay. This I can substitute here and I can compute my desired pitch, roll and yaw rate. Okay. And when I write this first type of formula, you may not able to here D, I can assume my derivative is 0. Okay. So now I am feedback what I am giving the, so still I have to work with some of these angles, but the some terms has reduced as, and now I am working with the feedback in the rate. Okay. That also I am using from the gyro, so not the attitude. So that we have done, and then we'll see some. Okay. Okay, that was the implemented. Sorry, I morning by mistake I have deleted 2-3 slides. I thought it is repeated, but that's what I have done. Okay. Now we check the performance. So it's starting from the ground and circular trajectory. Okay. And we have what we have done. Okay, this is a position and Euler angle. So we are attitude feedback it's giving, it's okay. Then what we have seen, just we have compared. If we assume body rates are similar to angular rates or they are not same, so with and without. So with see performance, when we do switching, it suffers. It's track pretty good. And as a control engineer, when we'll see here, we will claim that it's good compared to this. Okay. Oh, yeah, slide is there, just only my misorganization. I put after that. Okay, so that was the idea. Okay, so you decouple these things using the diagonal matrix, and these things PD, QD, I have already told about how to compute it. So you are now rate feedback you work. And then we compare our performance. Whenever we design some algorithm, we have to compare. That is, they ask what is benchmark. So it's always choose PID, because if we want to show superiority or we want to abuse something, PID is freely available. No one claims that PID is belongs to them. So we choose PID and choose this particular trajectory. Okay, omega. These are the states, and now we will change the frequency of omega, like frequency of the trajectory, and see the performance. So omega is chosen like this, PID and our proposed design. Okay. So our proposed design does good and PID does not do good. If it was ulta, we have not shown it. We have tuned it. We have done in a good way. Okay. And then we'll tell, see PID, the control commands you see, because of approximation. Jokes apart, because of approximations, there are jerks. Okay. Control is not smooth. And the moment control is not smooth, our actuator cannot produce that. It's not desirable. So next we have seen, we increase the frequency, PID fails because of approximation. I told it's valid only in the limited or flight regime, not the for whole flight envelope, but our approach works. And then control signals are also smooth. Okay, not bad. Next, we cannot say that always my control algorithm is best. It will fail somewhere. We further increase the frequency. So by simulation we can see up to what frequency. So what it demonstrates, this exercise, it works better than PID, but for not all the operating. So it has own limitation, and that limitation comes from physical model. It's not the control design itself. Okay. So this we have done. Now, how much time is left? When is supposed to end? 12 o'clock. Okay, we have time. Enough. So do you have any question before this is just that reference, the outermost loop I have told that I'll talk it about, but do you have any question on the control design. See, we have done in this process I have told about stabilization and tracking together. And before I move to this, say if you see in schedule I have told backstepping and I have wrote something also. When they ask me to what will you teach, I have written something, okay, this looks interesting, so more people will come. But when I am teaching, I am not teaching you backstepping, robust design, and I am not telling you anything adaptive. Okay. So before I conclude on this point, see, we can, if you know, if you have, I believe you have a control background, you must have heard about backstepping also. So backstepping by design is robust, right? And adaptive part will also have, why don't we use this adaptive things? Oh, sorry, backstepping. Why I am just even I have borrowed the slides from Professor Beraj's student, he has done on backstepping, but I was so lazy to put on the slides. Why don't we do backstepping? Even one of the students, Swati, she has done the adaptive backstepping for fixed wing aircraft. I thought I would put her slides, but later I dropped the idea. But just for as a conclusion, I want to put why not backstepping and why not sliding mode? See, dynamic inversion is the reason is dynamic inversion is very intuitive to understand, very simple. You have seen only with one order, second order aerodynamics and with one first order aerodynamics or couple of first order aerodynamics, we were able to design things. So it's very simple too. Backstepping has the advantage, it is robust, but it come on the cost of. We want our system dynamics in the strict, strict feedback form. And that, see, when we wrote the state space model, that was not available. Okay, so to apply robust things, we have to make some approximation and bring into some simplistic form, and then apply the robust things. But that is okay, you can do. If you have a robust design, it will handle these things, whatever assumption, it will compensate for them. Why don't see now issue when we have designed a controller, we assume in dynamic inversion, the plant model is known to us. But in exactly, say there is not much aerodynamics is there, but still there could be uncertainty in the moment of inertia or aerodynamics uncertainty, although you have plotted this RPM versus thrust curve and this torque things, this uncertainty could come, okay, and some this CG imbalance and other things come. So how do we take care of this uncertainties? And there will be a matched uncertainty in sliding mode also, like from control side. So see, there is a two approaches if we want to see uncertainties. When come uncertainties, so first we'll say adaptive things. In adaptives, there is again two. One is structured uncertainty and another is unstructured uncertainty. Structured uncertainty, we assume that parameter is, we know nominal parameter and there is a variation in parameter. Okay. So there is a part of unknown dynamics. So we don't know that unknown dynamics. So, but we are control engineers, smart again. So what? We know the control design. Everyone has, I think, no Leuenberg observer, right? So what we'll tell, we learn the unknown dynamics using the philosophy of Leuenberg observer or using the neural network. So the reason why I have not covered, already Professor Bera has covered the adaptive part. Okay, so you can employ somewhere neural network, Lyapunov approach to learn the unknown dynamics. Once you know the unknown dynamics, that is part of your actual dynamics, you can apply extra controller, that is known as the adaptive controller to stabilize system. The other approach is that you know, okay, this is my parameter and I know the uncertainty or it's a bounded uncertainty. What is a bound on the uncertainty? And I can use the robust controller. Okay. So in this way, so you are used to free, but the objective is to find TLMN. Once you have a TLMN, you can find the pulse width, PWM. Okay. So with this, I finished the discussion on Quadrator. Next, this is interesting for me, And we some of, I think audience also are asking, like they want to work on multi-agent system and cooperating. So this is a cooperative target capturing. So okay, with these pictures you can work with robots, you can work with the Quadrator or fixed wing UAV. So the idea is there, we have a evader and pursuer. Okay, dog or rabbit, like Professor Ghosh told, dog or rabbit or pursuer evader, this game you want to play. You want to play this game and you want to implement on Quadrator. And why I am telling Quadrator, I have taught you Quadrator. So how do you solve the problem? Okay, so my assumption is that when I start the game, I am not powerful from my enemy, or pursuer and evader are equally capable. So if I give you 2 persons which are equally capable and you ask them to fight, what would be the result of that fight? Or what do you think? So we put in then a ground, open ground, they can do whatever, but both are equally capable and they can sense what other does. Okay, what do you expect? Anyone can answer, including my student now. Just see intuition. Don't compel me to cite some example. Bhishma and Arjun, I put in Bhishma and Arjun. See if they are, you can, like I can now have made the assumption both are equally capable. So if there is a fight between them, what will happen? No results, right? Until unless open domain. And now I'll put the constraint. Okay, I put 2 dogs equally capable in one. What do you think? One is trying to evade and another one want to capture. Is it possible or not possible? The underline is they are equally capable. Okay, so what I am essentially telling, so we have this whole, I give you 2 quadrators and same control algorithm is there, they know motion of each other, and one quadrator want to capture another quadrator. Why do we require this application, or why do we want this algorithm? Just see in border security. Nowadays unmanned air vehicle will be deployed for border security patrolling. Okay, so unfortunately India is always surrounded by some nice neighbors. So maybe we have to capture their unmanned vehicle, or they have to capture our unmanned vehicles, for just surveillance purpose. We don't want to get captured by them or get surveillance by them. Okay, what do you expect? Same type of, because see, UAV is a class of vehicle, they are almost same. Just intuition, can you tell? Will capture? No or yes? There is a yes and no also. So okay, see, one cannot capture, we will put 10. we can do cooperative. That's why cooperative is there. Okay. See, if they have a similar capability or same capability, may not alone can do the job. Okay. So we have to put more. So that's why I have given the cooperative thing. So mathematically, how can I define the problem? So I believe you will be happy to see these equations. Okay, yesterday or day before yesterday you must have seen. Did Soumya you use similar equation? Even Soumya used this equation. Okay, so x dot equal to v cross phi, y equal to v sin. So each of vehicles using this model, and this is a model for simplistic model. As a guidance person, you can use this model. You have a liberty. Okay, but as a control designer, I cannot use this model. So if now I want to relate this problem with my control design. Okay, first I think whatever I am assuming, whether it will be implementable or not. So say this, when I propagate this model, I will get x, y and psi. Okay, so if you remember that block I was extreme left, I was saying reference input will be x, y, z and psi. So z I can make the constant Okay, I am telling the game is happening in the plane. It need not be necessary for simplistic case. We have taken the three dimensional also. Okay, it's on the planar game. So the objective is that if one of pursuer come close we define what is close, then we'll tell the capture is occurred, otherwise the evader is escaped. Okay. And what is other assumption? So if we assume this is a quadrator type, first is quadrator type model. That means vehicle can instantly move in any direction, free to. It's holonomic system. Holonomic means in any direction it can go. Okay. So now the idea is to solve the problem. So we also assume the game is playing in the closed domain. That's why I defined this one. So everyone has equal capability and game is, so we use Voronoi partition approach. You may have heard, you may have not heard about this. What is Voronoi partition? It's very simple. Say whatever your enemies is there, you draw a line and one equator. Okay. So you do with the all your enemies. So this is the equator, line of equators. This is a safe reachable area. So no one in this area, no one can come faster, can reach any point before this agent or evader. That is safe reachable area. Okay. For pursuer, I can define, I have not shown, but this is a jointly safe reachable area. If evader want to go to any point, it will be get captured because some of pursuer will reach before that. So the idea is that now very simple. We know some area, this. If I make the evader's safe reachable area 0, it does not have any space to go. 1 inch bhi zameen nahi denge. That's what that. So that is the idea. So now I define my area. I know this all vertices. Okay, I can compute then change in area. That is all things is that change in area. Change in area is I can write now partial derivative. It's depend on the position of the evader and position of pursuer. See, these are the algorithms. Algorithm is our main job, not the code writing. If we develop the smart algorithms, smart algorithms require good mathematics. So change in area. So what is I'll tell in one live objective is that, see, area we want to reduce the 0. If my rate of area what should be positive or negative of evader. If I make somehow the rate of area negative, eventually it will become 0. That is the idea. And rate of area is depend on the position of pursuer and evader. That means how the pursuer is evolving and how is evader is evolving. And the total idea is pursuer choose this direction in the gradient, negative gradient direction. So see, I define the area somehow. So there will be some direction where I go, the area will increase. If I go in the inverse direction, the area will be decreased. So what will evader do? The pursuer will try to minimize the area or reduce the area. What will be the see, pursuer is trying to minimize the area or reducing the area. What will be the job of the pursuer? Evader. I am telling ulta again. Pursuer wants to reduce the area and make eventually to 0 to capture. And what will evader do? If evader can maximize, that is the best things, but it is alone. Okay, it is in unknown territory. It may not be possible for it. It is try to at least hold that area. Okay. So in principle or philosophy, it's trying to maximize the area. So what should be the control action? So as I told the gradient, so I want to compute the gradient. So I move the pursuer in the direction of the line of sight. You know what is line of sight and perpendicular to LOS. I perturb and numerically compute this expression for gradient. Okay. Next, I will define for only one pursuer and evader. I will tell what the one of audience told with one pursuer and evader is possible. That's what I am telling you. So if you are in the closed domain, one pursuer is enough because you can capture using this approach. So now problem is this pursuer and evader, this is a line of boundary, that means equidistance line. And if I use the following command, what is following command? I tell my pursuer, use the pursuit command. You have read pursuit guidance, right? Pursuit guidance, nothing. This is the center of the line C. If I point towards the center of line, eventually the area will reduce to 0. Okay, that is the idea. Or if it does not reduce, the separation between pursuer and evader will goes to 0. So the mathematical expression I have given this. So then if I use this command, I have to show that this is a pursuit law or this is an inverse gradient direction. So I compute the gradient, it's given like this. And based on my this definition, so these are just opposite to each other. That means if I apply this guidance law, it will move in the inverse gradient direction. Okay. Okay. So since control engineer, talk cannot be finished between lemma and proof. And again, I have a privilege to use at least a couple of lemmas. So what I am telling, the change of rate. So pursuer, if applies the proposed law and evader do whatever it wants, okay, the rate of change will be, area is I am showing, will be less than equal to 0 or only 0 if evader applies the following command. So what it physically means, I don't want you to follow this mathematics. Physically means if we consider only one pursuer and one evader, if pursuer is trying to minimize the area, evader should maximize the area, then only area can hold constant. Okay, that is physical meaning. Okay, if this happen, what I am telling, the separation between pursuer and evader will reduce and eventually will become 0. So I take the square distance, then Lyapunov concept, I substitute this area, and this is always less than equal to 0. Okay, so it will be captured in the finite time. Okay, let's see if the video runs. Oh, see, this is a equidistance line. It's trying to hold this area, not moving along, and it's coming. So intercepted. So only with one pursuer and one evader, it is possible. If we use multiple, it's good. Okay. So what, see, if only single pursuer was able to do, why did I tell cooperative? I told cooperative and solve simple problem of missile guidance in closed domain. I have not finished. Another example is see, cooperation is required, but see, capability is assumed same. Okay, so one thing is okay, only we can reduce the time of interception when the time, okay, in cooperative sense, but the problems become challenging. It was easy because we have assumed the holonomic system. The moment we give the turning capability, see, now I have assumed instantaneously it can turn in any direction. The moment I put the constraint no, you can turn only by limited angles, the problem becomes intractable. Okay, so now non-holonomic system, I tell the phi dot, I have a constraint on phi dot, you cannot evolve like anything. My quadrator has a limited power. You cannot do whatever heading. I cannot apply any torque, whatever you tell. It has a limited, because I have seen the RPM versus thrust curve. So from there, my constraint on torque comes, and the moment I put the constraint on torque, my heading angle constraint also come. That will put constraint on the movement of the quadrator. So that I have to incorporate. So now same idea I would like to extend for non-holonomic system. So when I do this, the problem was that problem is not mathematically tractable. For same velocity, equal capacity, I was able to get the equidistance line, okay, but now no. So I define set, safe reachable set. So if I compute that set numerically, it takes lot of time. It's computationally, even forget about control. Computing that set takes infinite amount of time, okay. And as the area increases, the problem, the computational time grow exponentially. So, and the idea is that, okay, if I assume somehow some magic algorithm is available, that area is that, so I have to solve min-max problem, okay. Now I am in game theory, okay, min-max problem. So set of pursuer is trying to minimize the area and evader is maximize the area, okay. This is the problem. So I have already listed one problem. The computing this set itself is a computationally intractable, and then this is a combinatorial optimization problem. Solving that becomes very difficult, and now algorithms becomes important. How you propose the algorithm? If you propose smart algorithm, can get the solution? This will give you definitely some papers. Okay. So we have proposed solution approach. So whole space we have discretized into some cells, okay. Now we told not each point we want to compute the area because it was computationally. So we given the centroid, okay. For centroid we will see whether evader can reach fast or pursuer can reach fast. That means we compute the Dubin's distance. Why Dubin's distance? Because it takes the curvature or turn radius constraint into account, okay. So if you are not into Dubin's, it's like car. If you want to rotate the take car, you have, if you are not heading in the right same direction, if you have to turn back, you cannot turn immediately like invert. You have to take the some turn. So physically like Dubin's distance. So Dubin's distance is again kind of, you don't have a exactly analytical solution, okay. Some numerical things is there, okay. It's semi analytical solution. So computing that is also numerical. So for each point we compute the Dubin's distance. So whether evader can reach fast or pursuer can reach fast. So this is a safe reachable set. That means evader can reach fast. So it's safe for it. But we are doing only for centroids. Number of points we have reduced now, okay. Other way, now min-max problem. Again doing this also we have to solve the min-max problem. So instead of solving min-max problem, we told, okay, solve the problem sequentially. So first pursuer will assume other are applying 0, it solve, and second pursuer knows the what control command for first, third will for first and second, and evader we gave the power evader. If the all evader will know the control command of the pursuer. That means their future action it will knows, okay. Because that approximation we have give some power to the evader also. So the solution does not become trivial, okay. Doing this, and we have done this in the MPC framework, receding horizon framework. What we are doing, okay, now I predict my things for next 10 step for 1 second and evolve the solution and give me the best solution, and I will do every step like this, okay. So with this we have got this kind of trajectory, and this is a safe reachable area. And if you some instances you see the safe reachable area is increasing. Why? This because of turning. The problem is itself like this, okay. And then we use, there was some issue because it was very computational intensive. We use, okay, this PPN law is very popular. Do you remember what is PPN? Pure proportionality. Professor Ghosh has introduced. Why don't we use? There is a simple guidance law. You find the line of sight, rate of line of sight, and with theta you apply. You don't have to do this all optimization. Can you do like this? So every UAV and then collision triangle condition. If you remember constant bearing formulation, that concept. If everyone try to achieve that, so some of pursuer may get advantage because if we try to. So what pursuer is applying a PPN law, and evader is applying the inverse PPN. Inverse PPN is collision avoidance. Professor Ghosh again have talked about. So you maintain the line of sight. One is the SIP, size of the SIP is increasing, another SIP of SIP is decreasing. So increasing part is for a pursuer and decreasing part for the evader. So that philosophy we apply, okay. And then we'll see last video. So we have 2 pursuer and 1 evader. Black is evader, so they are reaching close to each other. Again, capability is small, they cannot accelerate. If it was a missile, it could have accelerated. Okay, but now velocity is same, they cannot accelerate. Only what it will do, when it turns, they take the advantage and hit it. So intercepted. So successfully intercepted. So we have not given a single space. Okay. With this, I finish it. I am happy to take any questions.